Hi, it's me, Dr. Prasad Puthiyillam. It's a class number 13 of coordination chemistry. So, in the previous all 12 classes, explained about spin coupling, orbit coupling, spin orbit coupling, then so many magnetic behavior of coordination compounds. So, the next topics, coming topics are spectroscopy. So, before going to spectroscopy, I thought of covering all the topics that I covered and put it into a single slide, a single presentation. So, watch this video completely without a break. So, you'll get a complete structure or figure of or complete idea about what happened in class number 1 to class number 13. So here ls coupling, so there are to explain the spectral behavior as well as magnetic properties of compounds, not only coordination compounds, the spectral behavior as well as magnetic property, two types of coupling is introduced by the scientists. They are ls coupling, that is for atoms with atomic number below 30, and even certain transition atoms, second series transition atoms are transition metal atoms also follows ls coupling. Then for heavy metals like lanthanides and actinides, jj coupling. So jj coupling I'm not covering in this class, only ls coupling. So for the cases of only one electron, so example, hydrogen atom has got only one electron. Only spin angular momentum of individual electron is considered. Orbital angular moment of that individual electron can be considered, and total angular moment of individual electron can be considered to explain the spectra as well as the magnetic behavior, if any. For two and more electron, that is multi-electron system, we need to identify the resultant spin angular momentum, resultant orbital angular momentum, and total the resultant angular momentum of these electrons. So spin angular momentum of individual electrons coupled to form, or they combine, or they interact to form resultant angular momentum, that is represented as s dash. That is a vector representation. Orbital angular momentum of individual electron coupled to form resultant angular momentum by represented as L. Then this S and L, these two couple or combine to form the LS coupling term, that is represented as J, which is the total angular momentum. This type of coupling or interaction between spin angular momentum and orbital angular momentum, we call it as LS coupling or Russell-Saunders coupling. So Russell and Saunders, they were two famous astronomers, though they introduced this LS coupling term to explain the spectral behavior of many atoms. There are three steps in LS coupling. First one, that is spin-spin coupling to obtain the S values, then orbit-orbit coupling to obtain L values, spin-orbit coupling to get the J values or LS coupled values. So step one, that is spin-spin coupling. For single electron atom or ion, coupling is not happen because only one electron is there. There is no interaction. Therefore, the S value, it can be taken as the spin of electron small letter s. That will be half, plus half or minus half. That we consider as plus half here. Then for two electron atom or ion system, in the outermost orbital where these two electrons are present, which we call as the optical electron, not the electron which is present in the inner shells. The outermost orbital, which are, if they are not paired, or if the electrons are present in the outermost orbital, we can call them as optical electron, because these electrons in presence of light energy, they will jump to higher energy level, jump back and giving this spectra. So we call them as optical electrons. For example, two electron is there in d subshell, then the spin coupling can be calculated as s1 to s1 minus s2 to s1 plus s2. That means half minus half to half plus half, that is 0 and 1. So we'll get the coupled value as 0 and 1 for two electron system. If three electrons are present, like s1, s2, and s3 are there, then their spin values are half into equal half values. If we consider, imagine, then s1 and s2 coupled to get a s dash. Then this s dash is coupled with s3 to get the final s value. So s dash can be calculated in the same way: s1 minus s2 to s1 plus s2. The values from 0 to 1, that is 0 and 1 only. Then s dash, if it is 0 and s3 is half only, that means first s dash we got 0 and 1. If s dash is 0 and s3 is half, then if we couple them, we'll be getting a value half, that is 0 to half, 0 minus half to 0 plus half, that is half to half, that is half only. For s dash value n1 and s3 as half, then the spin coupled value will be half and 3 by 2, 1 by 2 and 3 by 2. Therefore we can say that we have 1 by 2, 1 by 2 and 3 by 2 which are the spin coupled values. Now, in general, if we have n number of electrons, then we can say the s values will be 0 to n by 2 if n is an even number, or s value will be 1 by 2, 3 by 2, 5 by 2, the integers, half integers, if by 2 up to n by 2 if n is an odd number. In step 2, that is orbit-orbit coupling, which is also known as a residual electrostatic interaction. Here we consider the orbital angular momentum value, that's L value. If L value equal to 0, that represents S suborbital. L is equal to 1 represents P suborbital, and so on. For two optical electron atom or ion with L1 equal to 2 and L2 equal to 2, that is d orbitals, two electrons of a d orbital, d suborbital, then L value can be calculated as modulus of L1 minus L2, that is 2 minus 2, 2, L1 minus L2, 2, L1 plus L2, that typing mistake again it is there. Therefore, it is 2 minus 2 to 2 plus 2, that is 0, 1, 2, 3, and 4 are the coupled values. For these values, L equal to 0, 1, 2, 3, and 4, it represents the energy states. Those energy states are given as if L is equal to 0, you represent it as capital letter S state. If L equal to 1, represent as P state. L equal to D, 3, F, and 4 represents G state. For a three optical electron system with L1 equal to 2, L2 equal to 2, and L3 equal to, that is d orbital having 3 electrons, then they are coupled to L1 and L2 are coupled to get L dash. L dash is coupled with L3 to get L. So L dash coupling, that is modulus of L1 minus L2 to L1 plus L2. Again, the typing mistake is there. That is 2 minus 2 to 2 plus 2. 0, 1, 2, 3, 4 are the values for L1. Now these are the values for L1, so it has to be coupled with the L3. Therefore, if L1 equal to 0, L3 equal to 2, the L value will be 2. If L1 L dash is equal to 1 and L3 is 2, then L value will be 1, 2, 3. If L dash value is 2 and L3 is 2, then L value is 0, 1, 2, 3, 4. And for L dash 3 and L3 2, L values are 1, 2, 3, 4, 5. And for L dash 4 and L3 2, the capital letter L values are 2, 3, 4, 5, and 6. Therefore, we'll be getting the coupled value, total coupled value as 0, 1, 2, 3, 4, 5, and 6. These are the states or energy states it represents. That is, 0 represents S, 1 for P, D, F, like that. It represents the different states of the energy levels of the electrons which they occupy. So that is represents 6 represents I, 5 represents H. Now the third step, that is spin orbit coupling. In the spin quantum number is S and orbital quantum number is capital letter L. Then L less coupling values J, it can be calculated as modulus of L minus S to L plus S. For two electrons of d subshell, that is S1 will be half and S2 is another half value, individual electrons, their spin values, and L1 represents the d orbital, that is value is 2. L2 is L2, it also represents 2. Therefore, S is equal to 0, 1. The spin coupled values are 0 to 1. And L, the orbit-orbit coupling values are 1, 0, 1, 2, 3, 4, which represents the states of S, P, D, F, and G. For L equal to 0 and S equal to 0, we'll be getting J value as 0. That represents only S. Therefore, for L equal to 0, S equal to 1, J value is 1. For L equal to 1 and S equal to 0, J value is 1. For L equal to 1, S equal to 1, the coupled value is 0, 1, 2. For L equal to 2, S equal to 0, the coupled value, LS coupled value is 2. For L equal to 2, S equal to 1, the coupled value are 1, 2, 3. For L equal to 3 and S equal to 0, J value is 3. For L equal to 3, S equal to 1, J value is 2, 3, 4. For L equal to 4, S equal to 0, J value is 4. For L equal to 4, S equal to 1, the J value is 3, 4, 5. For these are the values calculated with the L and S values 0 0 0 1 1 0 1 1, like that. Those combinations, the J values are also calculated. Now I'm not going in detail about that. We'll move back to some other concepts like spin multiplicity, spectroscopic terms, Hund's rule to arrange the spectroscopic terms in the order of energy, microstates, and the forbidden spectroscopic ground terms. So spin multiplicity, that is calculated as 2s plus 1. So we know how we get s for single electron. The capital letter S is equal to small letter s only. If two electron system or more than two electron system, we calculate the spin coupling value. That spin coupling value multiplied by 2 plus 1, that gives the spin multiplicity. For two electrons in a d subshell, s values are 0 and 1, that we just calculated. Therefore, for s equal to 0, the spin multiplicity value is 1, which represents a singlet state. If s equal to 1, the multiplicity value is 3, which represents a triplet state. Now, the spectroscopic term symbols. If you have spin multiplicity value, if you know the orbital quantum number, and if you have the LS coupled value, that is J, then we can write a spectroscopic term as 2s plus 1 LJ. So this is the way to represent a spectroscopic term. So in which 2s plus 1 is from spin-spin coupling, L is from orbit-orbit in coupling, and J is from spin-orbit coupling values. So initially I'm considering only the spin multiplicity and orbit-orbit coupling values. J values will consider at the end. In order to avoid the confusion, first you need to identify the term with this, and we have to arrange them in the increasing order, and there will be some state which are forbidden, which are not allowed. So avoiding all those, then finally we go for the J value. For two electrons in d subshell, spin multiplicity values are 1 and 3, which we represent as singlet and triplet, two energy levels, singlet energy level and triplet energy level, that is obtained for two electron with the spin multiplicity values. And L values are 0, 1, 2, 3, 4, which represents S, P, D, F, and G terms. Therefore, we can write the term symbols as S1, P1, D1, means, or we call it as a singlet S, singlet P, singlet D, singlet F, singlet G, triplet S, triplet P, triplet D, triplet F, and triplet G. So these are the terms that we can write with spin multiplicity and the L values, that is orbit-orbit coupling values. Now, whether these are arranged in a order of their energy states. To explain the stability or their energy states, it was explained by Hund's rule. Hund's rule says that if a term with the highest spin multiplicity value, it will be having the lowest energy. That's why when we write electronic spectral arrangement, the term with the lowest highest spin multiplicity value should be there as the ground state, or that will be the having the lowest energy, or that is the more stable form. Therefore, multiplicity 3 is there, spin multiplicity 3 is there for all these terms. Therefore, these terms will be having higher preference, or they are having higher stability than singlet terms. Now, if these multiplicity values are same, so here we can say all these are 3 only for G, F, D, F, P, and S, then which one will be the most stable one? Then we need to consider the L value, that is orbit-orbit coupling. The term with the highest L value, that will be having lowest energy. Therefore, the highest value is for G. Therefore, we can say that 3G, triplet G is among these are the most stable or having lowest energy. Then for the same spin multiplicity values and one and is missing, spin multiplicity and L values, then we have to check the J value to say which is lowest, having lowest energy. That will I'll explain in the coming slides. So we'll restrict here to this one. Now we need to arrange them in the order of their stability. Therefore, G3 will be having lowest term. This energy state we have to write as the ground state. Then this will follow. So triplet G, triplet F, triplet D, in this order the energy states are there. Now, among these, whether all these states are possible, or is there any forbidden states present in them, that we need to identify. To that, we have to check the microstates. So since it is two electron system in a D, we can find it out easily. Therefore, we know D has got 5 suborbitals, and their values, orbital angular momentum values, we calculate with in this manner: +2, +1, 0, -1, and -2 give the values. Therefore, two electron systems, say one electron in the first column and other one in second column. That is, it may be dxy to dyx. Okay. Therefore, if two electrons are arranged in this manner, then we can arrange, or we can write their L value and S values in bracket. We know the spin value S is calculated as the spin value. This is plus half and plus half. Plus half plus half, it will become 1. L value we calculate as plus 2 into 1 plus 1 into 1. That means here it is plus 3. Therefore 1, that is the LS values for this. That is the microstate actually. Okay, so first microstate we obtain like this. That means how a possible arrangement of these electrons, these two electron in these five shells. That is explained as the microstate. All the possible arrangement of electron, that we call as the microstate. Therefore, first one we got as 3 1. Now the second electron spin is downward direction. Therefore, it will be anyhow L value will not change. That is +2 plus 1. That is 3. Whereas S value will be changing. It will be half minus half. It will be 0. So likewise, one down electron downward spin and another downward spin, it become 3 minus 1. Now I will not give much explanation. I just represent the electron and write the LS value to save the time. Therefore, for this arrangement, it will be 3 0. For another arrangement, it will be 2 1, 2 0. Next arrangement, 2 minus 1, that is 2 0. It is 1 1. 1 1 means plus 2 plus minus 1. Therefore, it is 1, and spin values plus half and plus half, it becomes 1. Therefore, 1 1. Likewise, it is 1 0. So total, I think 10 microstates we got now. Now the next arrangement, 1 minus 1, 1 0, 0 1, 0 0, 0 minus 1, 0 0, 1 1, 1 0, 1 minus 1, 1 0, 0 1. That is 20 plus 21 microstates we got now. 0 0, 0 minus 1, that is 0 0 again. Minus 1 1, minus 1 0, minus 1 minus 1, minus 1 0, minus 1 1, minus 1 0. You can see each state, either the electron arrangement is shifted to other subshell, or the orbital, or the spin is deviate. The spin is either plus half or minus half. So all these states are different states. So minus 1, and the next one minus 1 0, minus 2 1, minus 2 0, minus 2 minus 1, minus 2 0, minus 3 1, minus 3 0, minus 3 minus 1, minus 3 0. So all possible single arrangement is done. Now it is pairing stages. So the electrons are paired in the +2 level, that is 4 0, then 2 0, that is 0 0. This will be minus 2 0, and finally minus 4 0. So there are total 45 microstates are there. First level it is 10 states are there, 20, 30, 40 and 5. There are total 45 microstates are possible for d2 electrons. So these microstates, this is what how I wrote the ls values to compare the forbidden energy levels. The microstates can be calculated easily if n is the total number of electrons that can be filled in a given suborbital. In case of d orbital, total 10 electron can be filled, therefore n will become 10. And r is the number of electrons actually filled. Here r was 2 because 2 electrons are there. Then number of microstate is n factorial divided by n factorial into n minus r factorial, will be getting the value 45. Therefore here I wrote this scheme to check whether all these terms are possible or not, whether they are allowed or forbidden energy terms. We'll check one by one. So here L represents, the S represents 0, that is L value, and 1 for P, 2 for D, 3 for F, 4 for G, and spin multiplicity 3, that means the S value will be 1, and 1 then S value equal to 0, because here this represented what are microstates represent, that is with the L and S. Therefore we'll take this one in the increasing order. We'll take the lowest energy level first, because that will be occupying the, that is will be occupying the lowest energy level. For the lowest one, 3G, the L values, L will be 4, G represents 4, therefore it is 4. 4 means the possible values are 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, and S value, that is spin multiplicity, from that we are getting S as 1, that is 1, 0, minus 1 states are there. Therefore if you combine 4 and 1, LS value, if you compare 4 and 1, that 4 and 1 value, it is not present in this microstate. That is, the 4-1 itself is not possible. That means this particular term, it is not actually available, or it is a forbidden term as per the Hund's rule. Therefore it is not allowed. Therefore that term we cannot use for writing the spectroscopic term as such. Therefore we'll have to skip that one. Then next one we'll check 3f. The 3f means L equal to 3, therefore 3 2 plus 3 2 minus 3 values are the spin multiplicity value is 3, therefore S is equal to 1 0 minus 1. Therefore the combinations are 3 1, 3 1 if it is there, yeah, 3 1 it is there, so we can start checking whether it is allowed or not. So the possible LS values 3 1 3 0, that is 3 and spin value 0, then 3 and minus 1, 3 and minus 1 is also present here, then 2 1 2 0, 2 minus 1 1 1 1 0 1 1 0 1 0 0 0 1 minus 1 1 minus 1 0 minus 1 minus 1 minus 2 minus 1 minus 2 0 minus 2 minus 1 minus 3 1 minus 3 0 minus 3 minus 1. These are the values which are possible with the dot combination. So all these are the possible energy levels for 3f. All these values are microstates are available. Therefore this is not a forbidden value, this is actually present. That's better term we can use. Next one for 3D, the triplet D, L values are 2 to minus 2, and S spin values are 1 to minus 1. Therefore the first possible value itself is 2 1. The 2 1, it is already, it was there, but it is already taken by the triplet F value, that is occupied. Therefore this is not allowed, microstate is not allowed. Therefore the triplet D is not available, or it is forbidden as per Hund's rule. Then triplet P values, P means L equal to 1, that is 1 0 minus 1, and it is triplet, therefore S value is 1, that is 1 0 minus 1 values. Therefore LS values, if you check, that is 1 to 1 or 1 1 1 0 1 minus 1, then with the 0 combination with S 0 1 0 0 0 minus 1 minus 1 1 minus 1 0 and minus 1 1, all are minus 1 minus 1, all are possible, are present here microstate. Therefore this is also possible, it is not forbidden. Then we'll go for triplet S value, triplet S state. L value is 0, because S represents L equal to 0. 0 means only 0 is there, but whereas it is a triplet state, that is spin multiplicity is 3, s value is 101. So 0 1 0 0 0 minus 1. So the first possible value itself is 0 0 1. 0 1 here it is not vacant, 0 1 microstates are not there, therefore it is a forbidden value, it is not allowed, therefore triplet s is also not allowed. Then we go for the singlet terms. For singlet G, L value, G means L equal to 4, that is 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, and minus 4, and S equal to 0. The first value itself is 4, 0. Possible values are there, that 4, 0 is there, therefore we'll continue checking the other possibilities. Next is 3, 0, 3, 0 is also present. Now 2, 0, 2, 0 is also present, 1, 0 is present, 0, 0, minus 1, 0, minus 2, 0, minus 3 0, minus 4 0. All the microstates are there for 1G, therefore it is possible state, it is a allowed energy term. For 1F, L equal to 3, 3 to minus 3, and S value is 0. The first possible value 3 0, right now it is not available, that is already occupied, therefore 3 0 value is not there, therefore it is not allowed. The 1F term is not allowed, that is forbidden value as per Hund's rule. Then we'll check for the next, that is singlet D. Singlet D means L equal to 2, that is 2 2 minus 2, and the spin value is 0 because it is a singlet, or spin multiplicity is 1. Possible LS values are 2 0, 1 0, 0 0, minus 1 0, when minus 2 0. All the values are possible, therefore this is also available, so we can use it as a spectroscopic term. Then next one, 1P, that is singlet P. L values are 1 0 minus 1, and S is equal to 0. The first possible value is 1 0. 1 0 it was there, but it is already occupied by the ground terms, therefore it is a forbidden, it is not allowed. Then finally only one value is remaining, microstate is remaining here, 0 0. I think that is will be taken by the singlet S. Yes, it is L equal to 0, S is equal to 0, LS value if you check, that is 0 0, it is also occupied. Therefore these are the possible or available allowed microstates, allowed terms that we can use compared with the microstates. Then for a D2 electron, with this terms, we can check out the spin-spin coupling and orbit-orbit coupling scheme. So spin-spin coupled scheme, we know we got a singlet as well as a triplet. Triplet and singlet is represented here. So triplet values are having lower energy, and singlet is having higher energy. So in triplet forms, which are the allowed states are triplet F and triplet P. And for singlet cases we have singlet G, singlet D, and singlet S. Now while orbit orbit coupling will further split into this, with the energy levels will split in with the orbit orbit coupling. With orbit orbit coupling we come to know that triplet F is having lowest energy and triplet P is having lowest energy, that is according to the Hund's rule. Then for singlet term splitting, that is 1G, singlet G, singlet D, and singlet S. So this is the order of arrangement of these coupled schemes or orbit-orbit coupling schemes. Then for J values, that is the term symbol is represented as a spin multiplicity L and J. The J values now we need to find calculator to complete the scheme as LS coupling scheme. Therefore, for triplet F, we know L value is 3, S value is 1. Therefore, J value we can calculate as a modulus of L minus S to L plus S. L minus S means 3 minus 1. 3 minus 1 is 2. 2 L plus S, that is 3 plus 1 4. Therefore 2 to 4, that is 2 3 4. Therefore J values are 2 3 4. J value we write under as under the L value, therefore we can write it as a triplet F2. Then triplet F3 and triplet F4, these are the values with the LS coupling scheme, or these are the terms that we write with after LS coupling. For triplet P, it will be triplet P0, triplet P1, triplet P2. And for singlet G, it will be singlet G4, and for singlet D it will be singlet D2, and for singlet S it will be singlet S0. So these are the further splitting of the energy levels with the LS coupling. Therefore, Honsrud says that the first two cases already discussed, spin multiplicity, spin multiplicity values are considered first, a higher value, then lowest the energy. Then if spin multiplicity values are same, then higher the L value, that will be having lowest energy. If same spin multiplicity values and L values are there, then we have to check the J value. For a suborbital with less than half filled electrons, lower the J values, lower will be the energy of state. Then for a suborbital with more than half filled electrons, then higher J value, lower will be the energy of a state. So these two conditions also we need to remember to further arrange the spectroscopic terms in the increasing energy levels. Therefore, further we can arrange them as LS coupling scheme, that triplet F, further we divide into triplet F2 and triplet F3 and triplet F4. Therefore, since the two electrons are there, two electrons in a d orbital, that is with maximum capacity is 5, or half filled means 5. So 2 is less than half filled. Therefore, J value, lower the J value, lower the energy. Therefore, triplet F2 comes first, then triplet F3 and triplet F4. For a triplet P0, triplet P1 and triplet P2 values. And for singlet G4 we obtained. Then for singlet singlet D2, and for singlet S0. So these are the further splitting of the energy levels with LS coupling. So now we got a more energy splitting with LS coupling to explain the spectral behavior. Now further, it has got microstates. Microstates are we already calculated. We checked the microstate for all. Or microstates can be calculated with J value as a 2J plus 1. So J values we know, that is here triplet F2 means J values is 2. Therefore 2 into 2 plus 1, that is 4 plus 1, 5 microstates are further possible. So these microstates, it will be MJ coupled value, magnetic field coupled values. Therefore it represents -2 to +2. So the different energy levels, further I am not giving the energy levels here. So 5 lines we can represent with the lowest value for -2 and highest value for +2. Therefore this triplet F2 can be further split into 5 energy levels, and triplet F3 can be split into 7 energy levels from -3 to +3, and triplet F4 can be split into 9 energy level. Triplet P0 can be split into 1 energy level only, same energy level. Triplet P1 into 3 microstates, and triplet P2 into 5 energy states, microstates, and singlet G4 into 9, singlet D2 to 5, and singlet S0 as 1. So these are the all the possible energy levels with their ground terms. Therefore, with these terms, one can explain the spectral behavior for a D2 electron as well as the magnetic property. Hope you understood this video. It was a little bit lengthy, but still it covered almost all the terms that I taught in the class 1 to class 12. Hope you enjoyed this one. Don't forget to subscribe my YouTube channel and support me. Thank you very much for watching this video, and have a nice day.